Hello, and welcome back, everyone. It's a new day, and we are delving into the captivating world of greedy algorithms. Whether you're just starting to learn about greedy algorithms or you're looking to freshen up your skills and sharpen your problem solving abilities, this video is custom tailored for you. I'm Ryan Rad, and in this video, we will cover everything about greedy programming, from its core principles to its applications, and why it's such a valuable tool in your algorithmic toolbox. Just as dynamic programming is a powerhouse in the world of algorithms, the greedy programming is another star that shines in the galaxy of efficient problem-solving techniques. Are you ready to embrace the greed of efficiency? I know I am, so let's dive right in. Here's the agenda for today. First, we will recap some of the key concepts and principles of dynamic programming to freshen our memory and set the stage for understanding greedy better. Next, we'll turn our attention into greedy algorithms. What exactly are they, and how do they differ from dynamic programming? We will demystify the term and explore its core characteristics that makes it such a powerful problem-solving tool. To solidify our understanding, we will draw clear distinction between greedy and dynamic programming. When should you opt for one over the other? But how do we know if our greedy algorithm is truly optimal? We will unveil this secret sauce, a correctness proof for the optimal greedy choice. Understanding this proof is key to building confidence in our greedy approach. Pure theory won't get us very far, will it? That's why we're going to get our hands dirty and dive into practical problem solving. We will kick off our practical exploration by tackling challenges like activity selection, knapsack, and the house rubber problem. Okay, so let's get into it. Dynamic programming. So let's do a quick recap on what do we need and when do we use actually dynamic programming in practice. So the paradigm of dynamic programming says there is some sort of divide and conquer structure. You are able to break down a complex problem into smaller ones, and then those smaller sub-problems do overlap. So that is technically the number one thing we need. And also there is an optimal substructure into your problem. So if you have these things bundle up together, that means we have a great opportunity for applying dynamic programming. When it comes to methodology, in order to understand the structure of your problem better, we said you're going to start with a brute force recursive solution, and then you apply DP. So you have two options, obviously. The memoized version, which is a top-down approach. In this case, you're going to look into your brute force recursive solution, and whenever you make a recursive call, you're going to first check, is this a new subproblem, or this is something I have computed or solved before? So if you have solved that subproblem before, you're going to identify that and you're going to just fetch the answer. If you haven't identified that subproblem before, you're going to go ahead and actually solve it. So that's one approach. The other approach was tabulation, where you apply a bottom-up approach. So this is where you kind of figure out, in order for you to avoid all the recursive calls, what should be the right order to navigate through all the subproblems. So in this case, we're going to start all the way from the base case, and then we're going to build up by going step by step and solving smaller subproblems or easier subproblems first, all the way up to the more complex subproblems. Okay, so that said, let's break down the key differences between greedy and dynamic programming. So I have a bunch of different category that I would like to kind of compare these two together. And I think the most important one here are decision making, optimality, and complexity. So when it comes to decision making, greedy algorithms make decisions based on current best option without considering the long-term consequences. They are opportunistic in a way. They choose what seems best at each and every single step. While dynamic programming considers the big picture, every possible solution, and then it tries to find the best. In terms of optimality, unlike dynamic programming, greedy does not guarantee the optimal solution in all cases. They may provide a locally optimal solution, so something that is close to an optimal solution, but it might not be a globally optimal solution. And when it comes to complexity, greedy is often simpler to implement and quicker to execute, while dynamic programming can be more complex to implement and may involve more computational time and space. All right, so something you need to keep in mind is what I see a lot of times is people trying to find a greedy choice or a greedy algorithm that is 100% optimal. And it's oftentimes not possible for you to find a greedy algorithm for a lot of problem. But remember, the point of greedy is not competing with dynamic programming. The point of greedy also can be where we actually care more about complexity than optimality. So let's say there is a dynamic programming in order to find the optimal solution, but it's going to take quite a lot of time, and we can settle with a suboptimal answer, something that is close to optimal answer if we can get it super quick, super fast. So this is also a great application of greedy programming. So greedy programming is not just just to find the optimal solution faster than dynamic. It's just technically a completely different technique, and you don't have to be worried about finding the correct optimal greedy choice sometimes if all you care is or all you need is a suboptimal or something that is close to an optimal answer. Okay. Now, with that said, let's actually get into a classical problem where we can kind of talk about greedy choices a little bit more and to make sense of things that we discussed so far. So here we are presented with a list of proposed activities numbered from 1 to n. Each activity has a defined start time Si and then a finish time Fi. Our goal is to maximize our fun by participating in as many activities as possible while avoiding any time conflicts. Formally, what we are aiming for is to find the largest possible subset of activities that are mutually compatible. So two activities I and j are considered compatible if their time intervals denoted as SIFI and SJFJ do not overlap. Now, here's a crucial assumption. Oftentimes when people deal with activity selection problem, they actually assume that activities are sorted monotonically in a monotonically increasing order of the finish time. That means the finish times F1, F2, all the way to Fn follow a natural progression. They are in ascending order. This sorting simplifies our task here and forms the basis for our exploration of activity selection problem. So let's dive into the details and techniques to tackle this particular challenge effectively here. All right, so let's take a look at, let's take a visual look at the things here. So we want to attend as many activities as possible. And I just presented you with a bunch, exactly 9 activities here. And when we say we want to attend as many activities as possible, by attending, we mean being there, attending the activity for the entire duration of that activity. So there should be no overlap between 2 activities that we select. Okay, let me show you one example of such an optimal set of activities in this particular case. So it turns out the maximum number of activities you can actually attend in this case is going to be 4 activities. So this is one optimal answer. But another thing you need to remember is you might have multiple optimal answers to the same question. So for example, some of you might be already thinking, hey, there is another set that is equally optimal to set number 1, but it's slightly different. It's equally optimal, but it may contain a different subset of activities. One of those examples is going to be, for example, optimal set number 2. So this is another optimal answer, which is different from the first one, but they're equally optimal anyway. And because the lengths of both of these optimal sets are actually 4. So that's the maximum number of activities you can attend here, right? It turns out there is actually another one. So here is a third set that is also as optimal as the previous 2 cases. So in all of these cases, we are looking into an optimal set of 4 activities that we can attend, and they do not overlap with each other, right? And that's the maximum number. So I don't think there's going to be any more here because these 3 are all I found. But if you can find an additional optimal set here, please feel free to put into the comment section. Okay, so what we're doing here is we're just showing you that the optimal answer is not unique. You might have more than one, or sometimes you might have several optimum solution, but we only care about finding one. So if you can find one with your algorithm, that means basically your algorithm works as expected. All right, so now let's actually approach this problem with a dynamic programming mindset first. So we're going to try to break down this big problem into smaller, manageable subproblems. Let's assume that activity AK is part of an optimal solution. In this case, we're faced with 2 subproblems. So for a second, I want to pause here. And so if you remember from our dynamic programming discussion, where we talked about the rod cutting problem, which is another very classical problem when it comes to dynamic programming. So what we were trying to say there was, okay, so we don't know what's the optimal way of cutting a rod into pieces going to be, but regardless, we have to make the first cut somewhere. And by making that first decision, we will be facing a sub problem that is smaller than original problem, and that's going to be how do we optimally cut the remainder of that initial rod. Okay, so what similarities you already see between these 2 problems we have here? So in this case, we have to pick activities, right? And therefore, maybe we can do something similar. So let's assume we will pick one activity somewhere in the sequence of original activities that we were presented with. So we were given a bunch of options in a sequence, and let's say we know what's going to be the right first activities to pick. And I'm going to call that activity AK. So activity with K index, right? So in this particular case, if I make that first selection, we are faced with 2 subproblems. Subproblem number 1 is going to be all activities that gonna start after activity let me put it this way. All the activities that actually gonna finish before this particular activity, AK, as well as another subproblem, all the activities that gonna start after AK ends. So technically you have two sets or two subproblem, one on the right side of AK and one on the left side of AK, right? AK is somewhere in the middle. So this approach actually gives us an optimal substructure and suggests that we can tackle this activity selection problem just like rod cutting using dynamic programming. And so let me also, in case it's not clear, let me also show you the formula here. So it's going to be, so we're going to look into the activity selection problem from index I to index J, right? Or activity I to activity J. And then we already made the first choice of picking activity K, right? Therefore, we're going to have two subproblem, all activities before K starts and all activities after K ends, plus 1, y plus 1, because your optimal set already contains one choice at this point, and that is activity K, right? And while we are talking about this, some of you might be thinking, oh, wait a second, but you were just saying that if you know what first activity is going to be a good choice and you're going to pick that one, then all of these things are going to happen. What if I don't know what first activity should I pick? Okay, so it's dynamic programming, exactly same as the same problem we had or hesitation we had with rod cutting. I don't know where I should make that first cut. Here, I don't know what is the first activity I want to pick. Okay, what to do? Try all possibilities, right? So we need to consider all possible cases for AK, and then we're just gonna take it from there. And we're gonna look into all possible cases, and obviously we should be able to find an optimal answer at the end of the day. Okay, so I'm not gonna focus on the dynamic programming aspect of this moving forward, because we just wanted to find the basically the optimal structure, substructure of this problem, but we're gonna focus on the greedy here, right? So we are not gonna come up with bottom up or top down approach, dynamic programming approach here. So the next thing we're gonna do is we're gonna focus on how can we apply greedy programming here, or what is a greedy choice to consider when we are solving activity selection problem. So we just explored the concept of optimal substructure for this problem. And now we are delving into the fascinating world of making a greedy choice to tackle this. But how can we do that? So one greedy choice that has been widely studied for this particular problem, we're going to tackle that one, which is the earliest finish time. So the core intuition here is to select an activity that leaves the maximum resources available for as many other activities as possible. In other words, we want to make choices that open up the most opportunities for additional activities down the line. And remember, since these activities are sorted in monotonically increasing order by finish time, the first compatible activity to finish is actually one way of thinking making this greedy choice. All right, so now what I want to do here is, or just in case this doesn't make quite so much sense to you right now, I would highly recommend making a pause here and just thinking about this and letting the idea sink in before we move forward. So all we are trying to see here is there is one possible greedy choice. We don't know if it's correct, and that's fine. We're gonna look into that, right? We don't know if that's correct, but we already have one candidate greedy choice that we are considering for the optimal answer of this problem. Okay, so what I want to do next is I just want to quickly walk you through a correctness proof for a greedy choice. So this is technically the way we do it with all greedy choices for all different problems. This is a type of proof that is called substitution, proof by substitution. So let's delve into the proof of the correctness of our greedy choice in the activity selection problem. This proof will help us solidify our understanding of why this strategy might or might not work. Okay, so I already have the entire proof for you in this slide, so I'm not going to read this, but what I want to show you instead is going to be something visual, more interesting, and probably a lot easier to understand. Okay, so bear with me here. So again, I have the exact same set of activities I show you initially. I have 9 activities here, and you can see when they start, when they end, they have different duration. And suppose that we're going to define a bunch of variables visually here. So suppose SK is the entire list of activities, and we have an optimal subset of activities, and we're going to call that one AK. And I'm just going to also bring that into this picture. AK is one optimal subset, okay? A subset of the original problem. Now, please note that there may be more than one optimal subset, and we just saw that with the previous example, okay? So let's introduce a key element here, J. So as you can already see, activity, the green activity, we are actually naming that to J. We're calling that J moving forward, and this is the activity within AK with the earliest finish time. So let me repeat that. J is one activity in AK that has the earliest finish time. Now, we have 2 different scenarios to consider here. Before considering these 2 scenarios, I just want to draw your attention to another naming that I have here. So I have X. If you notice, I have a yellow activity, which is activity number 1 in this case, and I'm actually denoting that as X, and that is my candidate greedy choice, right? So X, among all the activities we have here in SK, in the original entire set of activities, X is my greedy choice because X finishes sooner than any other activities, right? So X is my candidate greedy choice. And then J is the activity with the earliest finish time within my optimal set. Okay, so we have 2 scenarios. If J is same as X, then we're done because we just show that the greedy choice belongs to the optimal solution, right? And it could have been the case, but it's not in my example here. So if J is not equal to X, then we need to consider an interesting action here. We need to consider a new set of activities. We're going to denote that as A prime K. And in this new set of activities, we essentially replace the first activity in our optimal subset, J, with our candidate greedy choice X. Okay, why we do that? Well, okay, so first of all, let me actually do that, and then I'm going to explain what are we trying to achieve here. So if you're defining another optimal set, oh, well, we don't know if it's optimal yet, right? But we're going to call that A prime K, and the only difference between AK and A prime K is the fact that I'm just going to remove J and I'm going to bring in the greedy choice here. Why I'm doing that? So the key idea here is, or with any substitution, proof by substitution approaches that or attempts that we do, is that we want to show if your greedy choice is not part of the optimal solution, if you bring it in, your optimal solution remains as optimal. So that's the idea. So we want to see how much damage potentially this greedy choice can make if we bring it into the optimal case. If it remains as optimal, that means greedy choice belongs to the optimal answer, right? But we don't know yet. Okay, so how many things do we need to check for? Number one is compatibility, right? Did X actually mess up with the compatibility of activities in A prime K? Let's see. So the thing here is, activities, you need to note that activities in A prime K are all disjoint and compatible. Why? This is because the activities in AK were all disjoint and compatible, right, by definition. And since J is the first activity in AK to finish, and X is the first one in the entire set, so there is no way J can beat X in terms of finish time. Therefore, A prime K is also a compatible subset of activities. So there we have it. In terms of compatibility, there is no problem now with in A prime K. How about the optimal answer or the size of this subset? This might seem very obvious, but we removed one activity from AK, right? And then we replaced that with something else, right? So we removed one, we added one, therefore we still have, so it's technically like the original AK had a length of 4 activities. A prime K had 4 minus 1, right? And then plus 1, which is going to be 4 again. And the beautiful part about A prime K is that it includes our candidate greedy choice, which in this case, I'm going to drop the word candidate because that greedy choice actually was proven to be an optimal choice for this particular problem. Now, with that said, you need to be very, very careful when it comes to finding or actually doing greedy programming, especially when you're expecting your greedy choice to lead to an optimal solution. For activity selection problem, shortest duration, picking the activity with the shortest duration or longest duration or earliest start time or latest finish time all lead to non-optimal solution. And here is an interesting thing to look at. How about picking the activity with the latest start time? How about this? Is that going to be also non-optimal? So think about this for a second. We are trying to pick the activity with the latest start time. What does that mean? That technically means you are trying to leave as much resources on the left side of that activity, right? So it turns out this is technically identical to the earliest finish time, and this also going to lead to an optimal greedy choice. And if you want to prove this, so this is going to be a very good exercise. If you want to prove this, try to prove it exactly how we did prove the earliest finish time. And you should be able to actually show that that's also an optimal greedy choice for this particular problem. Another common question that I see sometimes people are struggling with is going to be, is greedy top down or bottom up? Well, let's answer this question super quickly here. Greedy can be actually both. It's top down when approached recursively, and it's bottom up when handled iteratively. But here is the key takeaway here. Greedy isn't about the order. Whether it's top down or bottom up, it's all about the strategy, the greedy choice. So let's see an example. We already came up with a greedy choice for activity selection problem, right? So now what we're going to do next is let's code it up and see how it works in practice. So we're going to try to see how recursive greedy solution works for activity selection problem one step at a time. To begin with, we're gonna need to define a hypothetical activity, and I'm gonna show you that this is harmless. And let me do it first. So what I'm gonna do here is I just define A0 activity with index 0, and then this activity starts at in the past, sometime in the past, and then it's going to end at 0. It's going to end at the present time. So this is something happened in the past and has no conflict of any kind with any of the actual activities we have here. And most importantly, we're not going to take any credit, or we're not going to count this toward the optimal solution. Okay. And why do we need then? Why do we need this then, though? So the reason we need this is because like the algorithm that I have for you is like such a common algorithm or pseudocode that you see, I think in a lot of places, and I see a lot of people get stuck with this because they are like, the initial basically. So the way this actually works is the first initial call is going to be with k equal to 0, and then you won't be able to execute line number 2 unless you actually had created previously an extra hypothetical activity that's going to end before the first activity. So this is just a quick trick to make this pseudocode work. But if I were to do this or write this actually code again, I would technically just start from I think k index number 1, and because you have to pick the first activity anyway, right? So remember, the activities here are in a monotonically increasing order of the finish time. Therefore, you gotta pick that first activity anyway, and that's gonna be your greedy choice, right? And you gotta pick that first activity anyway. So again, whatever that makes more sense to you. So for this particular pseudocode, we need that hypothetical additional activity, and then the first. So here's the thing. Also, let me quickly define the variables here. The index k here denotes the subproblem of sk to be solved, and then the n is the size of the original problem. And remember, again, activities are monotonically increasing order. Therefore, all we need to do with this code is to find the first compatible activity. So what's going to be the first compatible activity? The first activity that's going to start after our current selected activity in the optimal set ends. That's technically it, and that's what we're doing in line number 2 here. So the first initial call to solve this entire problem is going to be SF011. That means the size of your original problem is 11, and then what else? And then the index of the subproblem is 0, so that means the entire subproblem, right? So what my point was, we can actually start with 1, right, if we just change the pseudocode and make our first choice. But because this is recursive, so it might work a lot better with the tweak that we just did here. But anyway, so this is how things gonna get started, and let's take a look at things visually. So you're gonna look into your basically at the very beginning, your k is 0, your m is going to be 1. So you're going to check whether a1 is the first activity that's going to finish and is compatible with a0. The answer is yes. So we're gonna stop the search right there, and we're gonna pick a1 as our basically first entry into the optimal subset. And then we're going to keep going. So our second recursive call is going to be now with k equal to 1. And what does that mean is we're going to look into all activities, starting from the second activities, looking for the first compatible activity. Okay, so we're going to start with A2. Is A2 compatible with A1? The answer is no, so we continue our search. So we're going to go to line number 2, line number 3, and we continue our search. And we're going to look into A3 now. Is A3 compatible with A1? The answer is no, and we move to A4, and then finally we found something that is actually compatible. So we're going to pick A4, and then we're going to make the next recursive call, which in this case is going to be for k equal to 4. And we're going to keep searching. We're going to start from A5 is not compatible with A4, A6, 7, not compatible, and then we find A8, which is going to be added to our optimal set of activities. And then if you want to do one more step, we're going to do another recursive call for k equal to 8, and then that's going to give us A11 as the next entry to the optimal set. So I'm not going to continue this, but yeah, actually we're almost at the end of this example, because we already have the 4 activities, right? And A11 is basically, we reached the total size of the original subproblem, and we have the solution here. Okay, perfect. The next thing we need to do is we're just going to show you, because we just told you that you should be able to make greedy work in a non-recursive way. So how that's going to work. So if you look at the structure of this problem, what we could do is we could just make the first choice anyway, because we know that the activities are sorted based on their finish time. And the first one has to be the first one that finishes, right? And therefore, we can make that choice first, and then we're going to move forward and just look for the next compatible activity, right? To be added to your optimal subset. And this way, you're not making any recursive call, right? Previously, we were calling basically the same function to solve the subproblem of a smaller size. In this particular case, we are just moving forward, and we don't actually require to do any recursive call to solve this problem. Okay, let's take a look at the knapsack problem. This is a classic challenge that has intrigued problem solvers for generations. What makes it particularly interesting is that it's a puzzle, or the greediest strategy does not always lead us to the optimal solution. However, with a slight tweak to the problem, we arrive to another variant of the original problem, and suddenly the greedy strategy becomes very effective. So let's set the stage and see what do we have here. So, like, first of all, we have a bag with a certain capacity, and then we have a bunch of different items. So let's say we have n items, and this might be like all different things, different value, different weight, and then our goal here is to decide which of these items to take to the pawn shop. Or you can also think about this as a situation where you're taking a flight and you have a lot of items to pack in, and you have very limited space. So what will you actually carry along with yourself? Each item represented by I has both a value, which reflects how much you could potentially sell this item for, or if you have to buy it at your destination, how much you have to pay for them, and then the weight, which is going to be basically something greater than 0 in all cases, and then that technically says how heavy this item is, and we don't care about the volume, right? In this particular problem. Now, there's a catch. Our knapsack, the container, actually has a limit on the amount of weight you can. So, for example, let's say your airline does not allow carry-ons to be actually heavier than, for example, 10 kg. And that constraint makes things interesting here. So the knapsack problem is all about finding the most valuable combination of items to take with you while adhering to the weight limit that we have, the capacity limit. Okay, so the next thing I want to talk about here is the two key variations of the knapsack problem. So we have this binary and fractional variants of the knapsack. In the binary knapsack, you can either take an item or you can leave it. So you take the item completely or leave it entirely. It's a take it or leave it kind of situation here. And however, this might not make sense for a different. I mean, not for every item, right? So let's say I have a blue hoodie here in this photo. So what probably doesn't make sense is cutting this hoodie by half and then taking just half of your hoodie with yourself in your next trip. And however, there might be some other type of things where the fractional knapsack gonna make sense. So in the fractional variant, you have the flexibility to take fractional parts of the item. So this means you can divide items into any number of pieces, and then you can take actually just a portion of that item. And then obviously you just have to be worried about that portion's weight and value. So that's going to make it a more versatile and a practical approach in some real world scenarios. All right. So now let's actually talk about what kind of greedy choices we can actually make for this knapsack problem. Something that you might actually think about would be taking the items based on value per pound. So you're going to look into, okay, so how much value do I get per pound? And the item that gives me the maximum, so that's going to be the highest priority item on my list. And I'm just going to take it from there and see how much space I have left. And then I'm going to look into all other items that I have. So if the supply of that item exhausted, and then if I still want to carry more, then I'm going to move into the next item with the greatest value per pound. All right, so let's see this in practice, because otherwise it's not going to make so much sense. So let's say I have 3 items here, and then you can see how heavy they are and what's the value of each of those items. And my knapsack here has the capacity of 50 kg, let's say. So we must select a subset of these 3 items shown here in this photo, and then we can do it in 2 different ways. So let's say we want to do binary knapsack. So if you're doing binary knapsack, what's going to happen is you have to go with take the entire item or just leave it entirely, right? So take it or leave it. You can't just be selective, and you can't basically have, you don't have the flexibility of just taking part of that item or a portion of that item. In this case, what are some of our options here? I think you have 3 options literally. So if you pick item number 1, which happens to be our greedy choice, right? So in terms of value per pound, $60 divided by 10, that's going to give you a $6 value per pound, which is greater than 5 in item number 2 and 4 in number 3. Okay, so if we take item number 1, then we have 2 other choices, right? We can either take item number 2 or item number 3, but we can't take both of them together because we're going to exceed the capacity that we have here. And so that's going to be 2 cases. But there's also another case here, and that is ignoring the greedy choice and taking item 2 and 3. And this is going to give us all the options we have here. So interestingly enough, the optimal subset includes item 2 and 3. And any solution with item 1 included, which is our greedy choice, does not lead to the optimal answer here. So here is an interesting observation. So we just realized that the greedy choice that we were just talking about and sounded quite smart does not lead us to an optimal answer here. All right. How about fractional knapsack? Let's try the exact same greedy strategy, but this time for a fractional knapsack and see what happens. Okay, so if we take that as strategy, that means take as much as you can from item number 1, and then take as much as you can from item number 2, and then see how much space you have left, and then take just a portion of item number 3, right? And then this is going to give us a total value of 240, which is absolutely optimal. So You can try any other combination for the fractional knapsack, and it's going to be impossible that you're going to come up with another answer that gives you a more optimal value here. Therefore, interestingly enough, we are seeing that greedy choice that we were considering is actually working great for the fractional knapsack, but it's not working great for the binary knapsack. And if you want to look into this intuitively, it might make sense to see that the choice of item number one gonna actually pose a limit on the capacity that you have and how you can play with the rest of the items. However, if you were to pick an item entirely, two suboptimal choices might together lead to a better solution than the greedy. So this is what you're seeing in the binary knapsack. But this problem never happens if you have the luxury and the flexibility of fractional knapsack. Okay, so because for binary knapsack, we won't be able to do greedy programming, right? What we want to do is we actually want to take a quick look into how do we solve the knapsack problem using dynamic programming here. Based on the code that I have for you, like pretty straightforward, look at my base cases here. If I don't have any capacity or if I don't have any items, then obviously I won't be able to pack any values, right? And then you actually look into the second section of my code here, profit one. So what is this about? So we're doing dynamic programming, and this is a brute force solution, right? So what we're trying to do really is, we want to do dynamic programming, right? So right now we're just doing brute force recursive. And so what we are trying to do is breaking the problem into sub-problems and then try all different possible ways to find an optimal solution. So in this particular case, profit number one, gonna look into the next item I have at current index, right? So what's going to happen is you're going to look into the array of items you have. Let's say the next item you have, or the item you have at the current index, is actually a blue hoodie. So what do I gonna do with this blue hoodie, right? How many options do I have really? Literally speaking, we have two ways to deal with this item, and one of them is going to be putting it into the bag. In this case, we used up some of the capacity we had, and then also we just dealt with the item at the current index. So two things happened. We used up some capacity, but we also made a decision and dealt with the item. Therefore, sub-problem would be capacity minus the weight of the hoodie, and then the remaining items starting from current index plus one. Okay, but we do have another option too. We could simply, so let's say I have the same item again, and this time what you could do is you could simply skip the item. In that case, the sub-problem has the same capacity left. The capacity not going to change because you just let go of this hoodie here. And then the sub-problem has the same capacity left, but what happened is we already dealt with the item at the current index. So your sub-problem gonna have one less item to be worried about, but your capacity is exactly the same as the as the previous step. Okay, so now we're gonna look into all other items that we have basically in the array, and then we're gonna go through the same decision-making process. And then at the end, we should be able to see what set of decisions or what combination of decisions gives us the optimal answer here. And so what particularly I want you to notice here is, let me actually show you the recursion tree for a knapsack. And what's happening here is we're going to get a sense of time complexity, but also I want to show you visually what happens. For every node, you have two branches, right? You can either go right or left. That's exactly going to represent and reflect the binary choice that we had to make, whether take the item or just skip it and leave it. So what's going to be the time complexity of this? First of all, you have n number of items, right? And then for each of those items, you have two options, right? So that's going to definitely actually get us to 2 to the power of n. And the other thing I also want you to notice is because we want to use dynamic programming very soon, but we want to have some motivation to do that. Why do you think dynamic programming the complexity of this solution is ridiculous, but how do we know dynamic programming is going to be any better? If you can identify any subproblems here, right? And so what are some identical subproblems here? Let's take a look at this recursion tree carefully for a second, because if you can't identify the subproblems here, we have a problem. Okay, so let me help you out. There are two subproblems here, right? Only two. Why? Because the tree is very shallow at this point, right? If you have more items, if you have a bunch of additional items, this tree gonna grow a little bit deeper, and then you're gonna see lots of identical subproblems that we are solving with this solution. These two subproblems are exactly the same. Don't worry about the selected items so far, or the profit we have made, or the value we packed in. Those are part of the solution, not part of the subproblem. What is part of the subproblem is the value we have left. And for both cases, we only need to be worried about item number D and the capacity we have left. So in both cases, we used up the capacity of 3, right? And we have 4 left. Therefore, these two subproblems are exactly the same. Okay, now let me show you quickly how a memoized version of that workforce is going to work. So first thing first, we're going to create a 2-dimensional array for memoization, and each element will be initialized to -1. And this is going to help us later down the road to identify unsolved subproblems. And then we're going to actually deal with our base cases, and then we're going to check, have we seen this problem before? Yes or no? If we haven't seen this problem before, let's solve it. And then we have our two kind of options here, right? Taking the object and dealing with the subproblem as a result of that, or leaving the object and the subproblem as a result of that. And finally, the best of both worlds, right? That's going to be your optimal solution. Okay, so now that we have the memoized version of this, since our memoized array, DP profit, length and capacity +1, store the result for all subproblems, we can conclude that we will not have more than n times c subproblems here. And by the way, n is the number of items and c is the knapsack capacity. So if we're only going to solve that many problems, n times c, that means our time complexity is going to be this much. And which is probably a lot better than 2 to the power of n, right? And then how about the space complexity? The algorithm that we just saw requires n times c space for memoization array. Other than that, we will use O(n), big O(n) space for all the recursion, basically call stack. And then, so the total space complexity will be n times c plus n in this case, which is asymptotically equivalent to n times c. So the space and time complexity are both n times c. Now, here things get interesting when we are trying to actually form a bottom-up DP solution for this problem. I only have part of the code for you because that's all we care and that's all we need. So our problem here, as you already noticed, is a 2-dimensional problem. So let's form a 2D table here. Let's call one of them capacity, one of them index, and then this way we do actually see how we're performing the recursive call based on the subproblems that we don't have the solution for or we haven't explored yet. Okay, so let's just go with one of these cells. let's say our current cell is DPINC, and that means dynamic programming algorithm solution for basically this particular problem at INC. So how much capacity we have left and what is the current index, right? And so the next thing here is just pay attention to what do we need in order to compute or solve this subproblem that we are interested in, and it's been denoted in gray. Okay, so we need two things, right? According to that piece of code that I have for you on the top, we need two things here. Number one is capacity. So this is the subproblem we need. Capacity minus weight of the current index, and then current index plus 1. This is the situation where the current item was taken, right? Was taken, and we put it into the knapsack. And so if you look at my two-dimensional space, this is going to be the red cell that you're seeing, basically southwest to the relatively to the location of the current position. Now, is that all? No. The optimal solution is the best of two things. What is the second thing? The second thing here is this subproblem, capacity current index plus 1. So you might already be able to locate this. This is going to be just to the south of the current cell. And these are the two cells we need in order to compute DPIC. We don't have them yet because we haven't explored them. Therefore, we have to make a recursive call. So the question here is, how do we change the order of the subproblems so we eliminate the need for making any recursive calls? And if you pay attention here right now, this is the order that we are trying to solve this problem. We start with N and C, and then we're just making recursive calls, right? And okay, so one way to solve this is going to be changing the order of the subproblem we're gonna explore. So if we rearrange this problem in a way that all you need in order to solve the current subproblem is the cell to the north and northwest, then we don't need to make any recursive calls, right? So let's see how this is going to work in practice again. So this is going to be the code for the bottom up. So as you can see, I have changed the order completely. We're going to start, look at my nested loop starting at line number 19. So I'm going to start with I from 1 to N, and we're going to start from C from 1 to capacity plus 1. So we're not starting from N and capacity. We're starting from 1 all the way to N and capacity. So that's the main difference here. But let me again show you this visually, because I promise that's gonna make a lot more sense. Okay, so in order for us to see this visually, I just have a very simple example for you. So something I want you to notice is we can actually populate the first row and column here with all zeros. And let me actually try to do that. And then I'm going to tell you what does that mean. So all we're trying to say here is if your capacity is 0, you can't make any profit. It doesn't matter, or you can't add any values, right? You cannot pack in any values to your knapsack because you just don't have any capacity, regardless of what items you have. And we can also do something else. And then for the second row, let's see how it works intuitively, because we only have one item, right? If you look at the second row, and things going to be pretty straightforward. So let's see that in one step. And so as you can see, because I only have one item, all I have to look at is, do I have capacity? Do I really have a choice here? So if your capacity is 0 or 1, you don't have a choice, because you need at least capacity of 2 in order to fit item number 1. And we're gonna have that when the capacity is at least 2, and then all the way to 5. Nothing gonna change because you only have one item, right? And you have the capacity for it, and so you're gonna take it, and that's gonna be a better value, right, than not taking it if you can afford doing so, capacity wise. Now, moving forward, I want you to see things step by step. Okay, so let's go by step number one. So let's say I have basically, I'm looking at item number 2. So I have 2 items here, and then my capacity is 1. So this is the problem. This is the sub problem I'm trying to solve with 2 items and capacity of 1. Okay, how does actually thing work out here? For item number 2, when you have capacity number 1, do you have a choice? Yes, the answer is yes, because you only need a capacity of 1 to fit in item number 2. But fitting item number 2 means you actually get the maximum profit of this item, and then plus your sub problem of deducting the capacity of 1, and then looking into the previous items you had and how you could actually do there. So in this particular case, we're going to look into the northwest of the current cell in order to fetch that value. So previously, if your capacity was 0, it doesn't matter that you have still item number 1. You just couldn't take it. So there's going to be 0 there plus 3. That 3 comes from item number 2. Therefore, that is basically my option number 1. Okay, I'm going to keep this 3 and I'm going to compare that with the other option that I have. What is the other option? Not actually picking item number 2. If you don't pick item number 2, your capacity is going to be the same, but you have item number 1 that you still can't take it because it requires capacity more than 1, right? Therefore, the maximum of 0 and 3 is going to be 3. That's going to be the solution to this sub-problem. We don't need to make any recursive call because we already had the previous cells and all the information that we needed. Okay, let's move on to the next cell to the right. And so now your capacity is 2, right? And we still have 2 items. Your choices are going to be not actually picking item number 2. In that case, that's going to be our option number 1, or the order doesn't matter really, but that's going to be one of the option. So that means you have a capacity of 2, and then you have item number 1 to decide for. That is going to be the north cell to the current one. And okay, what's the maximum value you get there? 4. So I'm going to keep 4, and I'm going to look into the other option, which is selecting item number 2. If you select item number 2, you're going to get a value of 3 right away, but you're eating out a capacity of 1. Therefore, your sub problem is going to be north west of this cell. And how much we could make there? 0. So plus 3 from item number 2, that's going to give us 3, one option 3, one option 4. What do? You get the best, which is going to be 4, and 4 is going to be the answer to this problem. Now, let's go one more step, and we're going to wrap this up. So in the next step, what do we have here is your capacity has increased to 3. Your sub-problem has a capacity of 3 and 2 items, 2 options, right? Not taking item number 2, that's going to give us a capacity of 4. Taking option number 2, item number 2, that's going to give us a capacity of 3 plus 4 from the northwest cell. So the maximum of 7 and 4 is going to be 7, and that is going to be the answer to this sub-problem. Okay, I trust you can take it from here and actually look into other steps here, but you can see that with no recursive call, we are able to solve the knapsack problem in a bottom-up dynamic programming fashion. All right. Imagine a street with a series of houses, each containing some valuables, let's say money. The challenge here is to figure out the optimal way to rob these houses without getting caught. Each house, represented as I, holds a certain amount of money, and our task is to maximize our earning while avoiding alerting the authorities. But here is the catch. You can't rob adjacent houses on the same night they have, let's say, some sort of security systems that is connected, and it will automatically contact the police if two adjacent houses were broken into on the exact same night. So now, how can we plan our heist to maximize our taking while adhering to this particular rule here? Okay, so the formal definition of this problem would be: given an integer array nums representing the amount of money in each house, return the maximum amount of money you can rob without alerting the police. Okay, so how do we do this? So let's see an example first. So let's say the array that you have actually represent 1, 2, 3, 1. That means that is how much wealth or money we have in each of the 4 houses in the neighborhood. You can see that the optimal value here is actually 4. I mean, if you're thinking 5, well, 2 and 3 cannot be broken into on the same night, right? Therefore, 4 is the maximum amount you can actually get by getting into the first and the third house. Okay, obviously without alerting the police, right? Now, so the other thing I just want to quickly mention here is that, so the house rubber does not quite depict an ethical or educational scenario, but the problem framing here makes it interesting to learn and discuss this problem. Now, if you're thinking, I don't want to rob people's houses, well, great, you're on the right track. But how else can this concept be useful? In programming, there are a lot of common patterns that reoccur in the problems that you see, and you can always apply a similar approach or similar solution to similar problems, but obviously as long as you can recognize them from the first place. So let's see an example here. You might actually face this problem in your interview. Budget allocation. Let's say you're managing a budget allocation for different projects within a company. Each project has a specific budget requirement, and each project is paired with an alternative project or plan B kind of thing. So it's essential to avoid allocating funds into 2 adjacent projects because they are technically there to serve the same purpose. You have to go with either this one or that one, right? And let's say let's say you will be given with a list of budget requirement for each project, and your goal is to determine what is the maximum or the minimum total budget allocation that can be achieved while ensuring that no adjacent project receives funds simultaneously. Okay, so this is going to be pretty much the exact same problem we are solving here, right? But with a much more ethical framing. Anyway, this might sound a lot more practical, but let's get back to that house rubber problem and see how we can actually solve it. So let's define Fk to be the optimal solution for the first k elements of the array A. Now, what's going to happen if, let's say, if you have F1, what does that mean? That means you only have one house to work on. So what is the optimal solution? What is the maximum amount of earning? Obviously, the value that is stashed in that house, right? So you have one house, and it's going to be A1. That's all we can actually achieve there. And if you have F2, this time you have another house, so you have 2 houses. Okay, so how many different ways you can approach this? So you have to either take house number 1 or house number 2, but you can't obviously get both of them because these are adjacent. Therefore, the optimal answer here is going to be maximum of the value that you get actually in either houses. Now, here things get a little bit more interesting. With f equal to 3, that means we have now 3 houses, more than 2. How can we do this? Okay, now there are more than one way or 2 ways to do this, right? You can either go with the first and third house, or you can stick to the middle one, right? Therefore, it's going to be the max of either the third and the first one, or just the middle one, right? Whichever combination or whichever set that gives you the better answer. Now we want to generalize this obviously to a more general scenario. So let's say you have n houses, right? So yeah, I have all these different houses, and now how can we do this, right? So how can we formulate this problem? So let's actually break this down. You already see a pattern, right? Or at least I hope you see a pattern here. If you don't, my recommendation is going to be continue picturing this situation for you. I started with F1 and then we continued with F2 and 3. Go with F4 and 5 until the subproblem, the structure of the subproblems are clear to you. But we can already see that if starting from Fn, basically, let's say we have n houses, for that last house, what are your options really? You can either break into that house. If you do that, then you have to, there are consequences for you, right? The number one thing is, if you get into house number n, you cannot be considering house n minus 1, right? And if you ignore house number n, then you can actually consider n minus 1, right? So technically, how we're going to break this down is going to be something that looks like this. So if you take house number n, then you can only look into the subproblems that contains all the houses except the last two, right? Because one of them you just actually got into that, the other one you can be considering. But if you're ignoring house number n, then you're just losing one, right? So you can look into what's the best value that I can get out of all the houses except the last one. Okay, so we have the structure that we are looking for. If you look at this formula, it's already a recursive formula, and we should be able to code this up quickly. But for those of you who are interested to actually see another variant of this problem, look into house number 2. There is also another house number 3. So I have the lead code numbers for you here so that you can explore. But let's code this up. So the bottom-up DP solution, I want to just go bottom-up right away. I believe we have enough, we explore enough dynamic greedy to be able to just do this one bottom-up right away. So what we're going to do here is we're going to look into the base cases first, right? And so technically, we're going to look into if there are no houses, obviously there's going to be no value. If there is one, then the value of that one is going to be the optimum answer. And then in all other cases, I'm going to define previous, so that's previous to maximum amount robbed from 2 houses back and backward, right? And then previous one, maximum amount robbed that can be robbed, right, from the previous house and every other houses before that. So what's happening here is we are technically just looking, we're starting from we're starting from the first house, so we're building this bottom up, so there is no recursive call, and we will be able to find all the optimal answers to every single problem and sub-problem here, right? And this is the exact same formula we have seen previously, but now we're exploring that with a different order. Okay, so the interesting part here is we're doing bottom-up dynamic programming here. That's good, and this is a space optimized, right? So this is a pretty decent solution right away. This actually gives you a super simple ON time and constant space solution, which is a pretty decent one for a problem of this complexity. But we just did bottom-up dynamic. What about greedy? Okay, so let's take a look at that. Can we get actually greedy here? We can always try. Why not, right? So any strategy that allows us to skip some subproblems and try to estimate or approximate a final optimal answer is a candidate greedy, right? Or a greedy choice of some level of optimality. So what I want to do here is I just want to show you a very simple greedy strategy. And so what you can think here is, why do I have to check all possible cases at every single step? Because I know I cannot be getting into adjacent houses, right? So what I can do here is I can divide these houses into two groups, right? Houses on basically located at even indices and houses at odd indices. So this is how it's going to work actually. If you take the first house, then you have to move to the third one, fifth one, right? So you're just taking every other houses, and this is going to give you two options. Okay, so is this greedy choice an optimal one? Well, let's take a simple example here. Consider the following array. I have 8, 1, 1, 9, 1, and according to this greedy code that we have here, this greedy solution, the answer is going to be the maximum of houses located at indices, the odd indices, right? So that's going to be 8, 1, 1, and then the even indices, which is going to be 1 and 9. Therefore, the max here is going to be 10. However, you can simply tell that the optimal answer here could have been, it is indeed 17, which is way better than the greedy solution that we got here. Therefore, this greedy solution is not an optimal solution, but it gives you an approximation, right? So if that's all you're looking for, an approximated answer, then this is going to do it, right? And this is going to do it in constant time, which is great. Anyway, so that's it about the house robber problem. And there you have it, folks. Greedy algorithms are like a breath of fresh air into the world of problem solving. They simplify complex challenges, and even when you can't find an optimum greedy choice, they often provide a solution that is surprisingly close to an optimal answer. You have not only grasped the fundamental of greedy programming, but also explored how they can be applied in real-world scenarios. But remember, the road to mastery is not a short one. It's about practice, understanding, and most importantly, the art of selecting the right approach for the right problem. Thank you for joining me on this topic today. Your support and enthusiasm fuel my passion for creating content like this. We have reached the end of our exploration into the fascinating world of greedy programming for now. I hope you had as much fun as I had walking you through this journey. Until next time, keep coding, keep learning, keep exploring. This is Ryan Rath signing off. Take care, and I will see you in the next video.